Digital PCR is the third generation of the well-known polymerase chain reaction amplification, where we amplify specifically a target and follow the evolution of a fluorescent signal in the reaction while the amplification takes place. The main advantages of digital PCR over qPCR is that it's an absolute quantification method, so you don't have to refer to a standard curve to quantify the target in solution. And it also presents an increased sensitivity. In principle, in digital PCR, we start with the same reaction mix containing eventually the targets in the reaction. And the key step is the partition. We will split the sample into a large amount of small compartments. And during that step, we will randomly distribute the target sequence in the compartment so that some initially contain the sequence and some don't. Then each compartment will act as an individual reactor where PCR takes place if the target, or at least one target of interest, is present in it. And in the end, it will lead to an endpoint fluorescent signal. And then, based on the number of positive compartments versus the total number of compartments, by applying some calculation with the Poisson statistics, we can estimate initially, the initial concentration of the target in the sample. At Stilla, we have integrated all this in a simple workflow. We're using microfluidic chips. We have two formats for different throughputs. And once you've loaded your chips with the sample, you just have to switch it from the first instrument, the geode, that will do both the partitioning and the thermocycling. And at the end, you will switch from the geode to the prism, the reader that will read the fluorescent signal. So the art of the innovation at Stilla is really the sapphire chips. It's already pre-filled with oil. It contains 4 microfluidic chambers here. So you load an input volume of 25 microliter of sample and PCR mix. And then in each chamber, you will generate up to 30,000 droplets. So it's a water in oil emulsion. And each droplet will have a volume of 0.59 nanoliter. The principle of droplet generation is what we call a confinement gradient. So the name was given before the COVID crisis. And it lies on the general rule that a non-wetting drop of liquid will resist confinement. So if I squeeze a drop between 2 flat surfaces, then it will exert a force on the confining plates to go back to its initial shape. Now, if I do the same, but on a wedge geometry, so imagine that I push the droplet into this wedge geometry, then it will exert a force that will make it propel outside of that geometry. And that's how it works in the sapphire chips here. We will push the PCR mix through a microcapillary by a pressure gradient difference between the inlet and the outlet port of the chips. So we'll push the liquid through the oil. There's no flow of oil. And then when the droplet reaches the end of the capillary, there's a slope. So that's the confinement gradient. And the droplet will propel outside of that geometry and then reach the chamber where they self-assemble in what we call a droplet crystal. So there's really a 2D layer of 30,000 droplets in each chamber. So during that step, we distribute randomly the target sequence in these droplets. And now we'll dive into what's interesting, our group testing study, where we have combined the high sensitivity of digital PCR compared to qPCR to see if we could tackle the loss of sensitivity we have inevitably when we pull several samples together. The study was performed in May in France at the Hôpital Bichat in the virology laboratory with Benoît Vissot. At that time, the positivity rate was evolving from 8.5% at the beginning down to 2.5% because of the lockdown restriction during that time in France. So we collected the sample. They were extracted and run through the standard method with the COBAS system for RT-PCR analysis. And we got an individual assessment in qPCR for those samples. And at the same time, we pulled them, so the sample, the nasal swab, together by group of 8, and then conducting an extraction. And then to get a group of 16 and 32 sample, we pulled a group of 8 extracts. And then we assess group of 8, 16, and 32 sample by digital PCR and compared the results with the individual qPCR assessment. To do the detection in digital PCR, we used a new kit that was developed by our Chinese partner, Apex Bio, during the Chinese wave. It's a triplex detection system that we also validated at the CNR at Pasteur. I didn't mention, but that's important. We have 3 detection channels with the NICA system, so we can detect 3 targets at the same time in one sample. So these are the results here. So let's first focus on the group of 8, where 35 pools were negative or included no positive sample in qPCR. 18 included only 1 positive sample in qPCR, 2 with 2 and 1 with 3 positive in the group. Interestingly, 6 out of the 8 late CT samples, so probably the lowest viral load, were ended up to be the only positive sample in the group. And we had a concordance with the reference, so the COBAS system, for 52 groups corresponding to 416 samples, included 32 RT-PCR negative and 20 positive groups, so included at least 1 positive sample. We had a discordance for 4 groups, so corresponding to 32 samples. We had 3 qPCR negative, RT-dPCR positive discordance, and 1 positive in qPCR that ended up in a negative group for digital PCR, with late CT in qPCR. To conclude, we evaluated also the limit of detection and the limit of blank of our kit for this method. We found a good limit of blank. So the limit of blank is the number of positive droplets that you can expect in a negative sample. We established also the limit of detection at 90%. We found between 30 and 77 copies per ml. This is at least 2 times lower than the Altona kit used for the comparison here. And now regarding the pool testing study, we observed a better sensitivity than qPCR for the group of 8 and a similar sensitivity for the group of 16. So the key takeaway message is that we believe that we have a low-cost mass screening method combining pooling and digital PCR. Of course, I thank everyone who was involved in that study, and I thank you for your attention.